Hi friends, welcome to follow up. Let's have a look at problem 95, unique binary search trees 2. So here we're going to explain a solution based on recursion. So here we are given an integer n. So we want to return all the structurally unique binary search trees, so which has exactly n nodes of unique values from 1 to n. So both the two ends inclusive. So we want to we can return the answer in any order. So here in the two examples, in the example 2, so this is just one node. So we just return the one tree itself. And in the first example, n equals 3. So the corresponding trees are given by this one and this one, this one, and this 5. So basically, you can see the root nodes here is 1, 1, here is 2, here is 3, 3, right? So here the constraints are the following. The n is bounded above by 8, right? So n is at least 1. So with that said, basically we can look at the coding part. So for this problem, actually, the strategy we use for sure is recursion. So the reason that we can first think of recursion is that so the tree, binary tree, or here in particular binary search tree, right? Binary tree or binary search tree here is a recursive data structure, abstract data type, right? So it's actually defined in a recursive fashion. So that's why we can first think of recursion for this problem. So this problem, we are dealing with binary search tree. So we need to know binary search property, right? Binary search property. The property is that so the left subtree, the node values, so it's strictly less than the root value, strictly less than the right subtree values. So this recursively holds for each subtree, each and every subtree. So this is the binary search property. So last we noticed that so we can iterate over different root values, and then we can construct the binary search tree recursively. So here in this video, first we are going to write a hyperfunction which basically generates the unique binary search trees within a range, and then we just call that function. So with that said, first let's look at the hyperfunction. So we can see this is a utility function, right? So let's define this. Let's just write it as f. So we accept left, we accept a right. So here this f basically generate all unique binary search trees with values in the bound with node values in the closed interval L and R. In other words, both L and R are inclusive. So as for writing recursion, so we know that we need to have a base case. So here the base case is the following. If L is greater than R, so in this case we return null, right? So here we want to return a null tree. And another case is that if L equals R. So in this case, so we just have one node, a single node. So we return this tree. So we return this tree node. So the value will be, you can write L, you can write R, same thing, right? So this is the base cases. And then we want to make self-call of this function and make connection with and walk towards the base case. So here let's initialize a result variable. So it's an empty list at the very beginning. So we want to return its final state. So here we can choose different numbers in between L and R as root values. And once we determine that root values, we need to construct the left subtree using values less than that root value, and construct right subtree using values greater than that root value. So here we are going to consider for each possibility. So for I in range, so we start from L and ending at R. So we write R plus 1 here. And then let's first construct left subtrees. Left side is going to be F. So we from L to I minus 1, because by definition this is the inclusive, right? So we need this right value to be strictly less than the I we choose. And the right side is going to be I plus 1 and up to R, right? So notice that due to the return format, this left side and the right side are two lists consisting of binary search trees. And then we are going to iterate. So for L in left side and for R in right side. So we want to connect things together. So we are going to construct a root. So this is the tree node. So the value will be I, right? This is the root value. And then we are going to choose its left to be the left. So here let me use left subtree, right subtree, to avoid using this L and R with the bound, right? So left equals left subtree, and right equals right, so right subtree. So this way we construct a root node, and its left subtree is given by this here, and the right subtree is given by the R subtree here. And then we can add this, so we append this to the results, and then we return the result state. So this is the hyper function. So this is essentially doing the call work, and for us we just need to call this function to return the all the possible binary search trees. So here the bound is from 1 to n, so we write 1 and n here. So this actually forms a solution format to this problem. So before we make any comments, let's first do a test. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the generic cases. So here, as we mentioned at the very beginning, so this problem is related to binary search tree, a particular binary tree. So as tree is a recursive abstract data type, so when we meet problems related to trees, we can first think of recursion to see if the problem suits the recursion technology or trick. Then for this problem here, it's important to notice the binary search property. So once we notice this binary search property, and then constructing all the structurally unique binary search trees is basically very straightforward. So with that said, basically that's about it. So notice that there's a similar problem as unique binary search trees. You can try that, and if you can do this problem, then this one, unique binary search trees, should be no problem. So with that said, thank you.